Hi everybody, welcome to AP Stats. Today we are going to be covering the 1.5 section of your 1.5, 1.6 notes. So we will be working on the graphical representations of quantitative variables. That means that we are going to learn how to create and interpret dot plots. We won't be describing shapes just yet, but we will make and interpret stem and leaf plots. And we will make and interpret histograms. And all of this is how to represent our quantitative variables. So let's start first with dot plots. We've got three types of graphs. Let's start with dot plots. Dot plots display each data value as a dot above its location on a number line. So there's some directions right here about what you need to do to make your dot plot. You can also switch and orient your dot plot vertically. It's kind of whichever makes more sense for the space that you have. So here is an example of a dot plot that you might see. It is in April 2014, managers from the city of Flint, Michigan decided to save money by using the water from the Flint River rather than continuing to buy water source from Lake Huron. Soon after, Flint residents noticed that the water coming out of the taps looked, tasted, and smelled bad. Some residents developed rashes, hair loss, and itchy skin. Authorities insisted that drinking water from the Flint River was safe. As part of its regular testing program, city officials measured lead levels in water samples collected from 71 randomly selected Flint dwellings between January and June 2015. Here are the data in parts per billion. Note, the U.S. EPA requires action if a water system's lead levels exceeds 15 parts per billion. So we have an example of a dot plot of real-life data. Notice that there is a number line at the bottom and then a vertical axis. A dot plot is a really nice way to organize numerical data or quantitative data. It allows us to see the distribution of all of those quantities to see if there's any groups or gaps. And then we will be looking into this as we go further throughout this unit. But there's one example. Next, we're going to make our own. So how healthy is plant-based yogurt is, for example, one. The Nutrition Action Health Later provided data on calories, saturated fat, protein, calcium, and total sugars for many popular brands of yogurt. Here are the data on the amount of added sugar in teaspoons in a single serving container for all of the plant-based yogurt brands. So we've got some data here. There was a typo. This said 10. It needs to be 1.0. So first of all, we need to make a dot plot of these data. We have a horizontal number line already set up for us. So every time we see a value, like 0, 0, we're going to put a dot over top of that value. And so we'll go through here and we will just put a dot above every numerical value, so 1.0. So I'm going to pause the video, finish this up, and then you guys are going to also check to make sure that your dot plot matches my dot plot. So coming back, here's our dot plot. Make sure yours matches mine. When you're making your dot plots, you want to try to make the dots be equally spaced above each other so that you can get a feel for the frequency and how the frequency of each number compares. Now for part B, now that we have our dot plot, we can look and answer this question. The American Heart Association recommends a maximum of 6 teaspoons of added sugar per day for women. Can we use the graph in part A to justify the claim that a majority of these plant-based yogurt brands have less than half of the AHA's daily recommendation for added sugar? And we're going to explain our answer. So we're looking for, can we justify that the majority of these plant-based yogurt brands have less than half of AHA's daily recommendation? Let's see, AHA's daily recommendation is 6 teaspoons. So half of 6 would be 3 teaspoons. So let's write that down. So half, hold on, let's think about this first. Half of AHA's would be 3 teaspoons. we're looking to see for a majority. A majority is more than 50%, and that means we need to see if more than 50% of our dots are less than 3 teaspoons of sugar, added sugar. So there are 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Here's where the 3 are. So are more than half of the dots less than 3 tablespoons? Yes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I would say yes, more than half of all the dots are less than 3 teaspoons, which we could use to make our justification. So let's see what that looks like when we write it out. First of all, we need to answer the question. So I'm going to say yes. We can use the graph to justify the claim. So number 1, we are answering the question. The question is, can it? The answer is yes. Now we need to justify that. Well, first we have to say that half of the AHA's recommendation would be 3 teaspoons. Since more than half of the dots on the dot plot are less than 3 teaspoons, we can use this to justify the claim. So again, we want to make sure that when we're answering questions with data, we answer every part with a reasoning and with evidence from the graph. So first of all, answer the question. We have to relate what the recommendation was to what we see on our graph. In the next class, we'll get into talking about the shapes and describing. So now we're going to skip ahead to the next part of our lesson, which are stem and leaf plots. So the second type of graph. Stem and leaf plots look like this line and a bunch of numbers. Every stem and leaf plot has a stem, so the stem will be found on the left, and a leaf on the right. It's important that the stem numbers go from least to greatest, and you're not skipping any numbers. So the stem goes 0, 1, 2, 3, 4, 5, 6, 7, 8. We don't skip any stems. Do not skip stems. It's actually really important in our data analysis whenever we see that there are stems that don't have any leaves. We call those gaps. So that'll be important to look for in a little while. The leaves need to also have numbers going from left to right in ascending order. So we have 0, 5, 5, 5. They need to be in order, lowest to smallest, going that way as well. And another important part is that there's a key. So in this case, for line 5, which is referring to this stem and this leaf, that is a 45-minute travel to work. So you could have a key that said for line 5 means 4.5. It could be for line 5 means 45. Or for line 5 means 400 450. It's very important to have a key. So make sure you don't neglect putting a key on there. So you want to mix the stems, add the leaves, order the leaves, and add a key. So here we have some information about athletes and their parents. We've got some information about the athletes are going to wear helmets. Their parents are worried about a risk of concussion. So we have data about the measurements of their head circumference for the players on the team. When you're making your stem and leaf plot, since you've got to order your stems, you want to make sure you can go from the minimum value to the maximum. So I noticed that I need to go from 20.8 to 26.5 and all the numbers in between, which makes me think that maybe I want to have a stem and leaf plot where my key is a decimal. We'll show like so 20 line 8 equals 20.8. So let's make a stem and leaf plot. Since I need to go from 20 to 25, I'm going to have my stems 20, 21, 22, 23, 24, 25. Then I need to find my leaves. So all the 20s, there's one here, and there's one there, and that's all the 20s. So I'll put an 8 here and an 8 there. For all the 21s, let's see, the 21s, 21.9, 21.7, 21.0, 21.6, and I think that's all the 21s. So I want to put those in order from the smallest to the largest. So 21.0 is the smallest, so I'll put an O here, a 0, and then 21.6, 21.7, 21.9. Did I skip one? I feel like there's a 21 somewhere. Oh, there was a 21.5. So I'm going to need to move the 6, 7, 9 over. So 0, 5, 6, 7, 9. It's really important those go in order. Then you just keep going. So I'm going to pause the video, finish up. I want you to pause and finish up your stem and leaf plot, and then we'll check in just a moment. So here is my stem and leaf plot. See if we have the same stem and leaf plots. Now, we made the stem and leaf plot, and you see how this set of leaves is really long? Sometimes when you make a stem and leaf plot, in order to see a better distribution of the shape of the data, some people decide to split the stems. Splitting the stems means taking something like 22 and breaking it up into 2 intervals. So that would mean, like, instead of having 120, you'd have 2 20s, 2 21s, 22s, 22, 23, 23, 24, 24, 25, 25. So you double the amount of stems you have with the same number. Write each number twice. Okay. The first stem, if there's a number in your data that would go from 20.0 to 20.4, you would include it in this line. But I notice my only 2 in the 20s are 20.8s. So I'll put those here and leave the first one blank. For 21, whoops, I didn't mean to erase that. In this first line, if any data falls from 21.0 to 21.4, I'll put it in the first line. If it falls from 21.5 to 21.9, I'll put it in the second line. And I'll continue with my stems for the rest in the similar manner for the rest of the data. So in the first line, I've got 21.0, and that's it. Then I'll have a 5, 6, 7, and a 9. I'm only using different colors right now just to show the differences in the numbers. Oh, I realized I didn't put enough 22s. Let's try that again, another 22. For the 22s, I've got a 22.0, 22.2, 22.3, and a 22.4. So 0, 2, 3, 4. And then on the second line, I have 22.5, 22.5, 22.6, 22.6, and 3 22.7s. For the 23 lines, there's a 23.0, there's two of those, a 23.1, a 23.3, and a 23.4, and then two 23.5s and two 23.9s. For the 24s, there's a 24.0 and a 24.2. And then for the 25, oh, need another one. I need a gap there. 25, there's a 25.6. So actually, let's see if I can squeeze those in here. 25, 25. 25.6. Okay, so when you look at the two, in this case, when we did split the stems, we get a little more sense that, hey, there is a little bit more of a data gap right here than there was before. Now there's some considerations. There's no magic number of stems to use, and if you split the stem, make sure each item is assigned an equal number of possible leaf digits. So that's why we're going from 21.0 to 21.4. When you have too many digits, you can have more flexibility by rounding or truncating. There's just some considerations to keep in mind. Another option you have when you're making stem plots is something called a back-to-back stem plot. A back-to-back stem plot is two stem plots that are placed back-to-back. So it's like if you want to represent data for two different groups. So here we have data for pulses of randomly selected group of students, and they've been separated into males and females. So I'll make one side of the stem plot be males and the other side of the stem plot be females. And I notice that the lowest value is 46, the highest value is 90. So that tells me my stems need to go from 4, 5, 6, 7, 8, 9. So now this means you can make a back-to-back stem plot to show one side of the stem plot be for the males and one side of the stem plot be for the females. That's another option you have. So for males, let's see, I have a data value 46, there's a 55, there's two 61s. Now I'm going left to right this time. So you want to make sure when you're ordering your numbers, they go from the inside out. Two 61s, a 68, and a 69, and a 72. And again, my key, we could say 7 line 2 is equal to 72. In this case, the 2 is coming from the 7, but you read it from the stem. You read the line from the stem outwards. All right, for the females, let's list those times. Any in the 40s? There aren't any in the 40s. In the 50s, there's someone with a 50 beats per minute pulse rate and also 52. For the 60s, let's see, I'm seeing a 63, a 60, let's pause it.
Generals, we have a few announcements for you.
So when you finish the female data, here's what you look. So we can see our pulse rates of the females in our group on the right side, 50, 52. Pulse rates for males on the left side, 55, 61, 69, and so on. Now let's talk about histograms. Histograms are for quantitative variables. The histograms are the ones that look like bar charts, but their bars need to touch because you're talking about an interval of numbers. So, for example, the little picture I drew down here, this could be an age group on the bottom and the frequency. So the first bar would represent those in the 0 to 18 age group. The second bar, 18 to 36. And the bars need to touch because the data that you're collecting are numerical and they're continuous. So you're not just counting the number of 18-year-olds. Anyone between 18 and 36 would fit in this category. So here's some directions on how to make a histogram. We're going to make our own using the tax rates from the 50 states. So here we have our 50 states and the list of the sales tax rate as a percentage from a recent year. So if you look through here, interesting, Alaska had 0%. Let's see, where's Kentucky? Kentucky had 6%. So we're going to make a histogram of this data. The first thing you need to do is you need to look at the data that you have. Our lowest number is 0. Our highest looks like it may be 7, maybe? And we need to find a way to break these up into intervals. So what you can do is you can find a way to break them up, kind of like the stems. So we have anything from the 0% to the 1%, from 1 to 2, from 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, and 7 to 8. So I'm going to go through here and count. How many times do I see anyone in the 0 to 1 interval? That would be, let's see, in the 0 to 1 interval, there's Alaska, there's Delaware, there's Montana, New Hampshire, Oregon. 1, 2, 3, 4, 5. So there were 5 states fitting that interval. And so then I would draw a bar going up to 5 from 0 to 1 and shaded it. And then I would continue to do this for the rest of my data. I'm going to pause and fill that in. So now I've gone through and I've calculated which sales tax percentages fit in which category. Here's my frequencies that I counted up. Here's my sales tax rates distributed in a histogram. So now I can see, oh, okay, there's a lot of states who have sales tax rates between 4 and 8%. Not very many have less than 3%. So we can use histograms to help justify our claims. In fact, we could even use our histogram to justify a claim about a majority of states having a sales tax rate of at least 5%. Well, 5% is right here. So can we argue that more than half of all of our states do that? So that we would just count and see if that was more than half. Visually, it looks like it might be more than half, but we might also have to say, count these numbers and add them up. And I think, okay, that's more than 16. So yes, we could use this graph to help justify our claim. We'll do a little bit more with histograms in a little while. Some considerations: the choice of intervals in your histogram. It can affect the appearance of the distribution, so it can look like some bars are taller if you don't have very many stems. But a good rule of thumb is you want to have at least 5 intervals, so that you can see get a good feel for the shape when you're making them. Do not confuse histograms with bar charts. Histograms are for quantitative data, and bar charts are for categorical data. And those are categorical data. We don't have those bars touching. Quantitative data, it's continuous or discrete. Numbers are continuous, so we need those bars to touch. All right, here's a chart we can use on when to use which graph. So sometimes you're going to have to make a choice. Should you use a histogram, a stem plot, or a dot plot? Well, all 3 of these are really, really good for quantitative data. It's just sometimes it's more practical to use a dot plot. Dot plots are great for discrete counting data with small values. Histograms are really good when you've got a lot of values and you want to break it up into intervals. Stem plots, you also like to have discrete data where you're counting so you're not trying to round very much or round off in big numbers. So take this into consideration when you're choosing which type of graph you want to use. And then I think that's enough for 1.5. So we will do 1.6 in our next lesson.